Okay. Okay. Okay, so let's resume the lecture. So last time we actually talked about some of the basic concepts of data warehouse and the data cube. So just to remind you that, for example, if you have 3 dimensions, product, in this example, product, date, and the country, the most fundamental parts of the data when you import it into the system, let's say there are only 3 dimensions, and the finest granularity is exactly as we've shown. So just to keep everything simple. So just assume that on the date dimension, the finest granularity is quarter, right? And the product is actually at the product level. In fact, if you look at the value TV, PC, and the VCR, again, this is an older example. Nobody uses, I think, VCR nowadays. But it's actually not a specific product by itself, right? So PC is not a single product. PC is actually a product category or subcategory. Most likely, this is more like a subcategory because all of them actually can belong to a category called electronics, right? So if you think about, if you ask a shop owner what kind of things you actually I can purchase, I mean you sell, right? So you want to start to enumerate each and every product on the shelf or in your warehouse. You actually will say, okay, we sell mainly 3 categories. Let's say food, right? Electronics, and maybe cleaning or whatever thing, right? So basically, within each department or category, you might have subcategory. In electronics, you have these kind of things. You might also have, let's say, gaming devices or let's say mobile phones, whatever. They all belong to the electronics, right? So let's say the finest granularity is actually, let's say, it's most likely a subcategory level. So basically, each and every value here, let's say here, essentially you load it from. So this, let's say we talk about the total dollars sold. Okay, so it's going to be a numerical value, and the value is actually aggregated from all the sale transactions which happened in the first quarter, and it's selling the item on the docket, if you remember, is actually belong to TV according to certain ontology or classification scheme, right? And it's actually sold in USA, so it's actually in any of the storefront in USA. Okay, so this is actually what is originally imported into the data warehouse, as you can understand. But with that, we can actually create other kind of data cubes. So one of the things, for example, if you look at the front end, these 3x4 orange kind of cells, each of the cell actually contain a number as well. Okay, this is actually a 3D example, but in 2D, essentially this part becomes the bottom part, which is usually the subtotal or subtotal, and this part will actually be the total. If you think about, let's say, salary by different department by different quarter, right? So basically, this is a natural generalization into 3-dimensional case, and this part, which is I just use slanted line to mark, is actually itself a data cube. In this case, it's a 2-dimensional cube, right? So it's actually a cube about the only 2 non-trivial dimension is date, which is essentially time, and the other one is actually country, right? So the product information is actually all aggregated. So you can imagine that, and by default, when you define the schema, let me remove these kind of things. When you define the schema, you actually can define an aggregation function. Okay, why you need an aggregation function is that, for example, the number here is 100, 200, and 300, just to make things simple. Okay, so you know that this number definitely will be 600, right? Okay, right? Should be correct. Yeah, this 600. So essentially, this actually says, okay, the total sale according to the first quarter and in all the shops in USA across all the products, right? I don't care. So that's why if you really want to put it, it's actually a special product called all, right? So this, again, it relates to, so we do have, all is actually very, you will see the occurrence of all later as well. But basically here, the all is actually at the schema level, if you like. This is actually defined hierarchy in the dimension. But as I said, so this all is actually, you can think about it's an instance. So we sort of abuse this notation, whatever name, a number of times. But it doesn't really matter too much. I mean, usually by the context, it's clear whether you are referring to an instance called all or a level. It's like a dummy level, which is called all. Okay. So if you really want to put it, we can actually borrow saying, okay, just imagine that we have a special product. It's right. It's a special product. It's called all, and so basically, literally, you are saying that the total sale for the product all in first quarter and in USA is 600. Right. That's exactly what we want. So the whole idea is that even if you do all sorts of aggregation on the white part, which you can only see from the top, you can actually get other kinds of data cubes. And they differ by different dimension. Some of them have 2 dimensions. Some have only 1 dimension. And this one at the bottom only have 1 0 dimension. And also because dimension is different, so the shape are going to be different as well. So this one is actually 3 by 4. This one is actually 3 by 3, right? So even if they are all both 2-dimensional cube. So last time we actually mentioned that, again, this figure does not directly correspond to this one because, yeah, they use different name. But you can actually draw the same lattice. This is a lattice for the cube like this. You will see that essentially that's the same because the top, by convention, we also put the more detailed one at the top. Yeah, it doesn't really matter, but it's just like in data structure when we draw a tree, right? For whatever reason, we actually usually the tree draws from facing down, right? So many people who learn the data structure for the first time will be surprised because the tree actually naturally goes upwards, right? But anyway, that's just by convention. So it doesn't really matter. I mean, if you swap everything the other way around, it still works. So basically, the key point that the top here is actually with all the dimension, in this case 3 dimension, and you can do all sorts of aggregation to get rid of 1 dimension. And by getting rid of it means you do aggregation along the missing dimension. Okay. If you still have problem, try to either you can use later especially when we talk about relational ones, you are going to revisit this figure again. But hopefully you can use whatever this kind of figure. If you have problem with working with 3-dimensional case, work with 2-dimensional case first. Okay, draw the lattice for 2 dimension. It will be much easier. It's actually this part. Let me use this color. Oops. It's actually this part, right? If it's 2-dimension, it's actually this part. Okay. So basically, you try to understand this and understand what's the difference between this cube and, for example, this one. Okay. Again, the arrow will explain later, but basically it says, okay, from the more complete cube, you can actually obtain any of the smaller cube where the dimension is a subset by using aggregation. Basically, that's the way we draw the lines. Okay, so given that, we actually will see that most of the operations, if you don't care about, just if you recall in relational database, right? They also have this kind of operations on relational algebra, sort of, to be exact. Basically, you have only a few very basic ones, like selection, projection, join. Join is actually not strictly not necessary as long as you have cross product. But basically, there are a few basic ones, and then you can do most of the things, but then they introduce more fancy things like group by, aggregation, whatever. It's much less discussed because, even in query optimization, even in the internal implementation, there are special considerations for the group by, aggregation, or whatever things. But the most fundamental ones, if you ever know database fundamentals, all the indexing and the query plan, let's say join algorithm, selection index, whatever, are designed around the basic operations. Okay, so what are the basic operations in data warehouse? For cubes, basically it's very similar to the relational database. So an operation takes a cube into as its parameter, and output is also a cube. But it's not a necessarily guarantee that the output cube have the same dimension or have the same shape. It's the same thing with the relational database, right? So if you have a relation of, let's say, one rows and three attributes, if you do a selection, it's one of the basic operations in relational database, you end up with a table. Again, everything is a relational table, let's say, of 10 rows and only two columns, right? So you actually change the shape, but it's still a relation, or it's still a table. Here, it's the same thing. So what you can do is that one pair of operation is actually roll up and drill down. So roll up actually means you start with, essentially, if we borrow this one and remove these kind of marks, basically roll up and drill down allows you to, so if you come from here to here, it's essentially roll up. Again, it's not up in this figure, but so it looks like a bit strange. But essentially, you are getting coarser granularity, right? So basically, why it's called a roll up is because if you think about here, you have product, country. So product and quarter still remains. So they are actually at the same level. Again, it's not. It's quarter, and it's product. Okay, so it's on this level, and at quarter, this is quarter, product, country. So I should have a country here. So previously it's at this level, this level, this level. So that's another way to showcase the current query. And if you roll up, you actually end up with a product, quarter, and all. So you move up in the hierarchy in the middle dimension, which is store dimension, because the previous level in the store dimension is country. So country is a fairly higher level. Now you move on to even higher level. So for example, if you have another level called a continent, then it's okay. I think it's called a region. But then if, let's say, we don't have this one, then we roll up to the next level, and that's going to be the domain all level. So, and whenever you have all, you don't necessarily need to put it here, okay? Because it's redundant. You can see that it doesn't serve any information. So basically, you drop it, and that's why you become 2. So that's why it's called a roll-up, although in this figure, it looks like going downwards. And of course, the other operation is called a drill down. Drill down actually gives you more finer details, right? Previously, you only have the summary information of the total sales by different product and by different quarter. Now you actually can decompose the number, each of the original single cell number, into 4 numbers. Let's say we have 4 quarters, where the sum of these 4 numbers are exactly the original number. Okay, so this is called a drill down. So this is roll up and a drill down. If you use this figure on the right-hand side, it's much easier to see why it's called a roll up and drill down. And also, it's generalized. It's better to, because the lattice, if you have more than one level, more than 2 levels on each dimension, especially for time, which is actually more like a DAG kind of things. If you draw the lattice, you can still draw it, but it's going to be very messy. Okay, I don't really want to do it. You probably want a computer to do it automatically. But basically, even if it's done, it's going to be a heavily, you got a lot of edge crossing, so it's fairly hard to see. But conceptually, it still doesn't work. It's conceptually, equivalent to say, okay, you move from, let's say, a cube here. If you move it to, let's say, product, if now you actually move to product, region, and month, then it's roll up because you actually go up, right? And from this gray one, if you actually goes down to day, it's actually drill down compared to the previous one, okay? Another two operation is essentially selection, okay? But they've got a special name called slice and dice. And essentially they are the same, except that syntactically, slice take only one condition, if you like. And the dice actually can, essentially is a multiple slice, okay? So slice is by the name of it, just like this figure shows. You choose a dimension and choose a value. Again, this is the most fundamental one, but you can choose a range, you can choose several values. But conceptually, it's a very simple variance. So the basic operation that you choose a value, and you just take out a slice where every of the cells actually on that dimension have that value as its coordinate, right? So literally just taking out the yellow piece. It's almost like slicing a loaf of bread and taking just one piece out, okay? So if you do, so for example here, we actually slicing, we can say, okay, now we do an operation where we slice the 3D cube on the product dimension with the condition that the value should be book 176, okay? So the yellow piece, think about what's the semantic, if you want to put an English description to describe the yellow part, what does it mean? It will give you the total sales. Again, we also talk about total sales in terms of dollars of that particular book 176, in all the months and in all the cities. Okay, that's the semantics. And to some extent, we don't care how many cities there are there, how many months are there. Okay, think about its span multiple years. Okay, and this operation is very good in the sense that you don't really care about the physical detail, but semantic-wise, it's very clear, it's well defined. But if you think about it, if you do it in SQL, things will be slightly more difficult. Okay, for a lot of reasons. We won't talk about too much in detail, but because we don't talk about query language, in the so-called MDX query language. The language will be very similar to this kind of slice operation. You just essentially you put a slice condition under the where clause. Where, for example, product dot from prod. So the syntax is actually dimension. I think the dimension is called a product, and then you go to the level. For example, books 176 is the product detail product. Let's say, because otherwise it's also called a product. Let's say product dot detail product equal to book 176. So that's the syntax. So it's you will, after you learn this kind of, if you got a chance to look at the MDX, you will see they actually corresponding to this kind of logical operation very, very naturally. So that's the advantage. You don't need to translate to another language, right? And the dice is actually saying that if you do this twice but on different dimensions. Okay, first of all, you can't do it on the same dimension, especially for this kind of equality selection, because once you take it out, essentially you, as you can see visually, you actually turn the input 3-dimensional cube into a 2-dimensional cube, right? Because every cell on the value actually have the same product ID, so it's essentially a 2-dimensional cube. So you can't slice again on the product dimension. Think about that value is cannot be further divided, okay, just like atom or like the smallest particles. But you can actually further do a slice on, for example, on the month, right? So basically what you get is actually here, and if you slice, for example, if you slice on the month, you actually get this one. Again, think about if you slice on a particular month, it's going to be, right, you can imagine it's going to be something like this. Okay, so this looks exactly like this. Okay, so you can actually go directly say I do slice, or if you want you put it I do dice on 2 dimension. One is product, the other one is month. Okay, but again in MDX it's essentially several slices together. Okay, it's all put under where. So you can where you have a condition on product dimension, you have another condition on month dimension, and that's good. That's good enough. And the last one is actually also very simple. It's called pivoting. Okay, so one of the motivation is that, again, that's the most common usage of pivoting, is that think about in the early days. I mean, it's not in the early days. I mean, one of the major use of this kind of data warehouse or OLAP is to produce reports or charts or whatever plots. Okay, for reports, the most widely, I mean, as I said, I mean, for plots, you can actually use color, you can use shape or whatever. You can sort of display something like 3D, I think up to five dimension, sort of. You can visualize it, you can plot it, although it's probably not the best way to really understand the trend or differences because of lots of things. But for if you really want to produce a report, for whatever reason, you only got two-dimensional screens real estate, or if you print out as a page, you only get 2 dimensions. So what if you want to display a cube of 10 dimensions, which is actually very common? Okay, so you have to say, okay, I can only afford to display 2 dimensions. So how do you do that? So you can imagine we start with 3-dimensional case. So this is 3-dimensional cube, and if you want to do the pivot on the city and the month, which essentially says, okay, I can't show you the 3-dimensional thing. It's too hard. I mean, for example, you can't see the number which is in the middle, right? Right in the middle, there is a number, but there is no easy way you can show it. So basically, I'm going to show you all, different kind of pivoting results. So you can actually pivot on month and the city. So if you look at this 3D one, city is this dimension, and the month is this dimension. So the one you actually show is the top. Imagine that you actually have, it's not the top cell, but imagine that you have another thin slice, which is actually on top of that plane, okay? And essentially, you start with empty ones. So you actually create, let's say, empty cells there, additional cell. And then what you do is that for each of the cells, for example, for this value, you actually aggregate all the value here into this value, right? So it's almost like a crop. If you imagine, if you didn't put it on top, you're at the bottom. That's the same thing. You actually crush all the number into that new cell, and they run some kind of aggregation function. So this value is essentially the aggregate over a bunch of values, and the value actually taken from here, taken from here, taken from here, here, and so on and so forth. Okay, so that's why whenever you define dimensions, again, there are some kind of default aggregation function, usually sum or average, but you can do max, you can do whatever fancy kind of things. But in most of the cases, sum is actually a very common one because most of the measures are summable. Okay, so that's what you have, and you can actually pivot on, for example, this part, right? So essentially, you are pivoting. In this case, you are pivoting on city and product. So essentially, you aggregate all the cells for the same product in the same city across all the quarters. Here we have 3 quarters, and you get a number. After you do the aggregation, you get a number. You actually get a 2-dimensional cube, and the 2-dimensional cube is essentially a table, which you can show. Okay. This is actually one of the common usage of pivoting. And another kind of pivoting is that it's actually simple. If you think about it actually happens in Excel. Okay. So basically, if you show, let's say, a table where, let's say, product is actually by the rows and time by the columns, and for some reason you might want to swap the 2 dimensions. You want to put the time here. So basically, originally you might have, for example, you have, in this case, Q1, Q2, Q3, and lots of products. So you have a tall table. Now you can actually pivot it such that you actually come with a fat table, which is Q1, Q2, Q3, and this is P1 up to P1 million. So this operation is another very common pivoting. because literally you imagine that, and you can do this for 3D as well, but basically you essentially you take it and you rotate it. Right? So again, this operation is very easy to do in MDX. In the standard SQL, it's really not made to do that. You can look up ways to do that. So that's why I think by the end of 1990 whatever thing, so basically starting from, I think either IBM or SQL Server, they actually introduced a new whatever keywords or whatever or functionality into SQL. I think nowadays it's supported by most of the major relational databases. It's just called a pivot and unpivot. Okay, won't talk about too much detail. You just search for pivot SQL and you can find the usage. Basically, they are borrowing the idea from data warehouse into relational database. Okay, because there are also demands in relational database to swap the row and the columns. If you think about it, in the traditional standard relational notion, row and a column are totally different things, because columns are schema, right? Rows are data, but especially in reporting and in some other applications, actually mainly in this kind of analytical applications, the rows and the column they are exchangeable. So this is actually a very strong signal to say that, okay, the relational model probably is not the best model for our application, because there is obviously a mismatch in terms of the logical operations, right? Anyway, so actually lots of the operation is already introduced into relational database, borrowed from data warehouse. We don't have time to do this, but you can actually think about, this is actually used to be a pretty good interactive exercise. Actually, there are forums you guys can discuss, and so it's a Telstra homepage screen capture many years ago. So it's definitely no longer like this. But you can actually use this one, or you can use the latest one. So you can see that there is no what is called national broadband, whatever. Now Telstra also have this kind of broadband service. So basically, this just to show you that this is because this probably give you some idea of what kind of. So basically, this shows what kind of business Telstra do, right? And a major type of business. Okay, we just assume that you are doing a data cube modeling for Telstra and for this kind of phone service billing. Okay, or it doesn't really matter. You can think about, okay, just for analyzing their revenue, you want to build a data cube. So you need to think about, okay, what are the dimensions, and what are the basically it's what are the facts, what are the measures, what are the dimensions. And if you want to focus on this one, let's say phone service billing, so you can ignore this kind of internet, Foxtel, whatever, right? But even for phone, at least you have mobile and a home phone, right? Which is landline, okay? And if you think about it, it's non-trivial. It's not a standard one. It's not like a supermarket example, which is pretty simple, okay? But anyway, this actually kind of is a representative demand from telecommunication industry, which is arguably one of the large indispensable industry in any country, right? There are also specialized this kind of data warehouse or data cube design for, let's say, insurance or logistics or whatever. So there are a lot of specific ones. But anyway, I think this domain is easy to understand. You can actually try and see all these kind of things. Okay. So let's quickly move on to the logical model. So as we mentioned, so far what we consider are all conceptual models. Okay, conceptual model try to capture the most important thing, and if you remember, in ER diagram, presumably you can actually, after collecting the user demand, you draw the ER diagram, and you can actually work on ER diagram and then show it to the end user. With some explanation, hopefully you can actually use this as a chance to get some feedback or whatever. So the general idea that the conceptual model should be easy to understand, and it should be fairly close to what user perceives. Right? So if you think about what we just mentioned before, that's why I always emphasize once you take out a slice, for example, what does it mean? So you can actually show that this is a two-dimensional cube, and once you define the like a basic concept like dimension, whatever, then user can easily see whether you ever need to query this kind of things. And whenever you design the levels, you can actually ask the user, well, does this satisfy your design? Need? Because it's so natural and close to the user demand rather than implementation details. Non-technical user should be easy to understand. So the logical model is really like you are ready to map the conceptual model to some kind of physical system, and each physical system have different kind of logical model. Okay, this is a step more towards the low level or the implementation details. So as I mentioned, I think at the beginning, we actually have two main approaches, and of course, there is a hybrid one, and I think the hybrid one is quite popular nowadays. But let's say, okay, in the especially in the old days, basically there are two schools of approach, and you can imagine that because this is also a data management task, so all the relational database vendors, they are eager to capture this new market. So basically, there is an approach where they extend the relational database to accommodate this kind of multi-dimensional model. Okay, so they introduce a few new keywords or functionalities, and they show that they can deal with it. And there is some, especially new vendors, new companies, they actually say, okay, as I mentioned before, there are some natural discrepancy between multi-dimensional model and what relational model can do. So they actually say we just directly have a system where they actually directly use multi-dimensional model, essentially the multi-dimensional data cube as the logical model. Okay, but anyway, we actually first talk about the relational thing. So the reason you actually need to convert the conceptual model into a relational model is because later you are going to use any of the relational database to implement it. You can use Postgres, you can use Oracle, you can use whatever. Although there are certain technical problems you need to come over, but basically there is no bigger problem as long as you conform to the logical, basically relations, right? So before that, we actually can talk about how to. So basically, the solution is actually something called the star schema and its variants. Okay, to motivate a star schema, we actually can look at another schema called the universal schema. So actually, universal schema also exists in relational database. Okay, if you dig into, although not many book or lecture slides talk about it, when you learn functional dependency, normalization, or this kind of topic, essentially one of the idea is that people actually say, okay, even in the ER diagram design, what we can do is that we can actually just design a universal schema, then purely use functional dependency and all the constraints, basically they are called constraints, identified by the user or designer. Then there is an algorithm to automatically derive a set of tables. Okay, if you remember, I can decompose. Let's say I give you an initial schema, and I tell you that okay, all the FDs, and you can actually have let's say BCNF normal form. If you still remember, or 3NF. Usually 3NF or BCNF is enough. We won't go into detail, but suffice to say that that's the general approach, because this is more like an automatic approach, and like starting from a single monolithic things, like gigantic things. Imagine that in a enterprise, you put all the attributes into a flat table. So there is only one table. Okay, it looks very formidable. But then, as long as you identify the functional dependency, or all sorts of, there are even, let's say, fourth normal form, fifth normal form, and there are even more complex dependencies or constraints. As long as you define all these things, they can naturally break up into smaller tables. Although in practice, usually we don't do that. We actually typically start with designing the bottom table directly. But then you also need to know a bit about functional dependency to avoid bad designs. So here, you can imagine that we actually put all the things we know about each and every facts into a single table. Then if we go back to the sales example, this will probably be one of the choices. So this this table have 1, 2, 3, 4, 5, 6, 7, 8, 9 attributes, right? And arguably, you can imagine that this corresponding to really everything we know about. Again, this is a simplified version, okay? Just pretend that we only have these kind of things. It's actually everything we know about each and every transaction. But then there are actually lots of problems with this kind of universal table design. From relational database point of view, basically there are a lot of functional dependencies. Functional dependency means if I know the value of one attribute over one tuple, I can actually determine the other one. For example, if I know the city is in Sydney, right? I uniquely can identify that the state must be in New South Wales, assuming that it's all about Australia. There are cities in Canada, in the USA, whatever, right? Similarly, you can see that for the stores, it's uniquely determined as city, right? Although I draw this on the value part, the functional dependency is really between the attributes. Okay, you will actually see that. So basically, there are actually functional dependency, and you actually have store. Again, it's hard to show, but basically the store, given the store and given the product, it uniquely determines the sold, dollars sold. Okay, this is because given any store and given any product, right, there definitely will be a unique number, which is the total dollars sold for that store on that product, right? So the number itself doesn't matter. It just asserts that there is only one number. So if you apply the so-called normalization, which is the relational way to deal with this kind of functional dependencies. Oh, by the way, if you have too many functional dependencies in one table, this causes a bunch of problems, basically. So if you do the decomposition, one of the things you can do is that you break the table into three. Okay? So one table is store, city, state. The other one is product, brand, and category. The last one is not simply sold, not dollar sold, number sold, and cost. So the last table is not only these three attributes. You need to add something more. What do you need to add? Yeah. Because if you just record a table for $40, right? There is a transaction. Your total amount is $40. Sold the 10 pieces of something, right? And the cost is actually 18, so I can calculate my revenue. But what is this piece, right? Where did I sell it? When did I sell it? I mean, when we don't have here, we just assume we don't have two dimensions. Okay? So basically, in this table, you need to add essentially this one, right? So in order to uniquely identify the sold, you also need to include the keys. The keys, which is store and the product. But store is actually, if you know the jargon, this is the primary key in that particular store table. And the product is the primary key in that table. So you actually only need to include these two as a foreign key. Okay? Again, this course assumes that you know the basic, relational base, you have keys, for primary keys, and you have keys, primary keys, and foreign keys. That's almost the basic things, right? So if you do this kind of design, you end up with this one. So here I added time because it's, if I add a time here, it's too hard to draw. I mean, the font would be too small. So basically, just imagine that now you actually add it back. So you naturally have time table, product table. So these are the essentially, if you corresponding to the logical model, essentially these are dimension tables. So these are the tables created especially for dimensions, and particularly each level. For example, if you look at product, so product, category, brand, and this one, this supply name is actually, yeah, it depends on the logic. But let's say the product. So product key. Okay, the reason they actually have usually just like in many relational database. For a lot of reasons, in many of the practical applications, they recommend you to use the there are different names There are series ID, auto key, or whatever. There are different names, but basically the database will automatically assign sort of like a pseudo ID to each and every tuple. Okay. For some reasons, it's actually recommended. I mean, you always use it for a number of reasons. So basically, here you actually create a unique. I mean, you can imagine this is either database automatically created ones, or you actually take over the control. You actually use whatever keys, because the actual product could be something like a very long description. So, but you probably don't want to use the very long description as a primary key. You probably want to use some kind of numbers, or actually some special type as the primary key. So this is actually the PK, the primary key. Okay, and then the hierarchy, the next level is category, and the next level is brand, and presumably the next level is all here. Okay, so all you don't need to put it here. So basically, these dimension tables. This is the dimension tables, corresponds very well to our dimension in the conceptual model, and the attributes usually corresponding to the levels in the hierarchy on that dimension. And but you actually have the liberty to include other things like product name, color, or other kind of things. You can include a lot of descriptive attributes that doesn't appear in the logical design, but it doesn't matter. Or you can imagine that with the color, right? Again, probably it doesn't make sense, but at least you can imagine that now on the product dimension, I have two hierarchies. Okay, one is actually by this product category. So you have product. Then the other one is category, and then brand, then all. So this is actually one hierarchy. You can think about there is another hierarchy which product go to color and go to all, right? If you like, then basically this is you can view this as having two hierarchies. But again, it's up to you. Even without this one, especially in relation database, it doesn't matter. You can query. They are just attributes in a table, so there is no actual barrier for you to query this in whatever way. Okay, as long as you use the right SQL. Yeah, you do the same thing for location and for time, right? Now the rest, which is usually a place to store the numerical values or the measures. So this is actually the measure. And these are the FKs, foreign keys, because it has 3 dimensions. For each and every fact, it needs to refer to the details of each and every dimension. Basically, this is what, where, and when, right, in this case, of this cell. And then every numerical description about this cell. And so that's the design. And this is called a star schema, because usually you draw, by the way, this is called a fact table. And all the other dimension tables are drawn around it. So basically, it looks like a star, especially if you have many dimensions. So this is called a star schema. Okay? So you can think about how many rows are there most likely by common sense. Okay, you can take reasonable assumptions. How many rows are there in each and every table? For time, let's say we keep 10 years record. And the finest granularity here is day, right? 1 year have 365, right? And 10 years, 3,000, less than 4,000. So this actually have less than 4,000 tuples for 10 years. It's already enough, right? Think about Woolworths, whatever, you keep 10 years sales record. And for products, how many products does Woolworths sell over the 10 years? Definitely more than thousands, right? It's not small shops. I think, yeah, I don't know if it's true. Anyone working, previously we have students working in Woolworths. They have an analytical team to do this kind of marketing. So I think definitely in the order of millions, right? Let's say we put 1 million. Okay, and location. So this is basically this is the shop location, right, for Woolworths. I don't know how many shops are there, but okay, at least this is, I think it's no more than 10,000. Because in Australia, the postcode is only 4 digits. And except for CBD, you don't build 2 Woolworths in the same suburb, right? That's my guess, okay? But roughly, even if you build 2 on average, it's going to be 20,000. So the order of magnitude is in this order, right? Now, what about sales? It's much harder to estimate, okay? But the thing is that if you think about, I mean, first of all, this sales is actually not each and every detailed transaction item, okay? Because essentially here, the units sold and the amount, let's say it's dollar amount, is actually for the total. I mean, essentially it's already aggregated data. It's actually the total sales on a particular day in a particular shop, basically it's called location, and for a particular product, right? But it's still going to be a lot, right? So you can imagine that if you really have so many stores, even if you have 1,000 active stores, right? And how basically you can estimate the number of items in average basket, right? Whatever. I think each day, I mean, actually you only need to estimate on given each and every shop, given a shop, and on a particular day, how many different kind of products are ever sold. If you really have, although 1 million could be historical, but anything on the shelf, I think in the order of thousands, right? It at most hundreds, I think, right? If not more, okay? Because you can choose different kind of brand of milk and whatever things. I mean, the reason they put for physical stores, they actually do a lot of data analysis, especially for these kind of supermarket, I mean, large enterprises. They really think about what item to put on the shelf, and of course, and where to put them. There are actually a lot of things you can manipulate. And you certainly don't. I mean, you certainly feel that for popular items, you definitely have more. You need to have more shelf space, right? And for things which, like daily consumptions, like bread and milk, it actually need to occupy more spaces. Okay, so this is at least millions, if not usually. Let's say it's actually hundreds of millions. Okay, it's actually a really conservative estimate. You can actually think about it. So the whole idea is that this one is actually 100 million, right? The next large one is 1 million. Okay, this is already for large enterprises, and in time is only thousands. This is actually also like 10,000. So the key point is that, and also if you think about the growth potential, right? Time only grows very slowly. After 1 year, you only insert another 300-ish tuple into the timetable. For the location, yeah, I don't think that they are expanding too quickly, right? There are some kind of physical limits. Doesn't make any sense to put 2 Woolworths in a small suburb, right? For large one, probably it makes sense. For the product, it might change the most frequent one, but again, compared to the sales transactions, it's nowhere to be compared with. So basically, you can imagine that to start with, the sales table, which is the fact table, actually is gigantic compared to all the dimension tables. And over the time, the difference will be even bigger. Okay, so that's why that's another reason we always put the fact table in the middle. So that's almost like the most important and most centric, most heavy one or whatever, right? And this also leads to the fact that we can actually, if you look at this design, this is called a star schema. And if you look at here, any of the dimension table, as long as you have a non-trivial hierarchy, like the hierarchy here, essentially, if you learn the relational database design theory, for whenever you have, for example, this product table, you can do further normalization. So if you really want to reach 3NF or BCNF, which is deemed as good enough design, you actually need to decompose this into 1, 2. If we only look at this hierarchy, you need to decompose into 1 table, 2 tables. We don't have all. So you actually need to decompose this into 2 more tables. So you need to put product and category, because given the product, you uniquely have the category. And another table is category and brand. Okay. Or maybe it should be brand and category. Anyway, that's the whole idea. So if you do further normalization on the dimension table, because there is no normalization you can do on the fact table. Okay, you can think about it. Then you end up with this kind of snowflake schema. Again, they change example. So this is the star schema. It has more dimensions. It has 4 dimensions, but basically that's the same thing. But you can see that now if you normalize, this one will actually only be the location and the city, and from city to state and state to country is actually in another table. Okay. In fact, you can further normalize this table into 2. One is city and the state, and the other one is state and the country. Okay. You can even further normalize it. So this is called a snowflake because this looks like snowflake. Okay. So roughly speaking, if you really have a deep hierarchy on one of the dimensions, you can actually do these kind of things. But if your dimension table is actually shallow, for example, for time, it's really make any sense. I'll talk about the reason. So it usually is not further denormalized. Okay. So basically, in relational database, the reason we actually need to normalize further to end up with something like a snowflake schema is because whenever you have function dependency, this will create problem whenever you do the update. And that's exactly the most rare thing in data warehouse. You usually do insertion. It's actually append or whatever things. You don't insert arbitrarily into the past. And also it's done by some kind of ETL script or special things where you can take care of all the possible shortcomings of not having a normalized schema. Okay, and also the other reason for relational database to do that is to save space, because otherwise, for example, if you look at location for this design for a particular city, let's say Sydney, you need to remember this is New South Wales for all the shops within Sydney. So this kind of Sydney belongs to New South Wales information is repeated many times. So it's a waste of time, waste of space. But given that this is only in the order of thousands, the space wasted is not too much. Instead, if you do the normalization, whenever you do the query, potentially you need to do a further join between these 2 small dimension tables. Okay, so that's really, in many cases, the saving in the space in the update is not good enough to justify the potential loss in the performance, because in the performance you need to do further joins. Okay, but again, that's an option you can consider. So finally, in really large enterprises, each department might have their own data warehouse or data marts, and finally they might integrate everything into a complete data warehouse for the entire enterprise. So in that case, certain dimensions will actually be common to several data cubes. So here you can see that this item, which is essentially the product, if you look at, anyway. So it's involved in the sales fact table. It's also involved in the shipping. If you buy anything on Amazon, definitely the sales cube will record this transaction, and it will. Amazon doesn't have pickup service, I think. So you have to, even for pickup, you need to record information about delivery. It's kind of delivery. So it's kind of shipping. So basically, if you are on the logistics department, you actually build internal shipping whatever data cube. So basically, you can share the item dimension, and there are other dimensions you can share, like time and so on and so forth. So in this case, basically it's no longer a snowflake or star, but it's more like it's called a fact constellation. So basically it's like several stars together, right? Sort of. But anyway, so that's the jargons. So there are some kind of let me see. Yeah, there are some kind of advantage of star schema is that first of all, the translation from the multi-dimensional model into this kind of relation schema is straightforward, right? And it's very easy to understand. And also, whenever you do the query, you can use the traditional SQL query to do that. So this actually, you don't need to learn a new language. We'll talk about some extensions when we go to the internal part. In fact, they actually generalize. I mean, they actually extend the standard SQL with a few words. Like they actually have nowadays they have pivot, they have rollup. I think at least in IBM DB2 they have rollup. You can roll up on a few dimensions. So it's really you don't really need to have as long as you have some kind of table like this, you can actually use rollup, and you can use cube by. There are a bunch of other words you can use. Okay, but anyway, the whole idea that even without using these ones, you can actually use the traditional SQL. And whenever you answer something, for example, find the total sales per product category. So that's a product category. So this is actually to say that we actually need to look at the category level. Category is a level within the dimension product in our stores in Europe. So so basically in conceptual model, you actually do a slice on the store location, and then we won't talk about the MDX, but basically essentially do a slice on the stores, and then you do a pivot on the category. That's all you do. So essentially, if you write it in MDX, another language, essentially you know how to do slice, how to do pivot. Then basically that's the query language you can use. But in SQL, you can still do the whole thing based on a particular schema. Usually we use star schema, but it's much more verbose, right? And it's less direct. Of course, I mean this is using the old join syntax. If you use join on whatever, and this is a natural join, so you can actually you can have a more concise way of expressing it. But again, it's a fairly it needs some kind of translation. So it's not less natural than thinking from the multidimensional perspective. But it's doable. Okay, let's have 10 minutes break, then we move on to the next part.其实这个 level 是那个 tutor 设计的，
那能问出
这个
问题吗？
这个不是，你听我说，就说这里面有些问题是编程问题的话，其实我们基本上我们也不 suppose， 因为这个编程不是 suppose 你学这门课自己能够编程事情。let me figure out， 就是说这些函数是已经给你的。这个 my find 是你自己写的还是？
是给的。
给的。
对，我就想知道它这个函数找的是返回的是它的位置，就是
然后这个 next token 也是那个。
都是您给的。那要是您不了解的话，能跟 tutor 问一下他，或者现在的大。
不是，你现在有什么问题？
就是我不知道它这个函数是干什么用，是干什么用的，我看不懂，我不知道跟那道题有没有关系。
实际上就是这个，包括我们的 project 都是这样的，就是说，我们提供一些 facility， 就是你可以用，当然就是我们会禁止有些东西不能用，特别到后面有些东西，就因为不然你就用外面已经写好的一个库的话，就全做完了。但是就说 这个东西这个名很明显，这是因为你用过 C 吗？
用过。
你 C 里面有个叫 string talk 这个函数，你C 编过程的话，你就知道这个实际上就是模仿那个 string talk 那个函数，然后它就是根据那个，它就返回 return 的 token 和剩下的，它就给定一堆东西，它给定一堆东西，它解释出第一个 token 出来，剩下东西继续返回，然后你就可以不停 repeat call。这个用法跟 C 的那个 string talk。C 那个函数叫 strtok， 对啊，就跟这个函数的用法很像的。然后这个讲穿了，这个我看很多学生他也没有用这个东西来做，因为就我说这里面的关键是说你怎么去，不是这个细节的问题，就是说你关键怎么去 approach 这个问题，对吧？
我有思路，但是我不知道他给这个目的上，我怕会遗漏一些重要信息，是不是他需要调这个函数数
？Put it this way 吧，整个这个 lab 其实你只要实现最后结果就可以，但是我们会有一些 limit， 就是说你不能，就是我前面说，主要就是说
调的包的
啊，对，就是你要自己写就行了。然后至于你怎么写的话，这都是非常 free 的，因为我们已经告诉你就最后我们只是做一些简单性的测试。
那我现在已经做出来前2问了，怎么 check 呀？就是等一下，在这儿。
就说你先告诉我你想要怎么去 approach 这个问题了。我记得第3问是求数高是吧？还是要你
第4问是求数，
第3问是求什么？
第3问应该是
return 一个 tree 对吧 ？pass 一个 string 对吧？对啊，
就识别它的字符串，
变成一个对，没错，这是一个基础，其实这个是个基础工作，我都不一定要。我们只不过其实我们真正要教你做的是第4问，只不过就是这个东西顺便把它拿出来，就这样的话就告诉你一定要先把这个 passing 先做掉，不然的话你
后面没法。
对，后面也能做，但是
就比较麻烦。
其实你不用这个数也能做，但是这又不是我们想要你做的事情，你懂我意思吧？
明白。然后这个，排程都有点忘了，当然学的可能也因为不太好。然后已经做完前2问了，然后不知道怎么测试。虽然我是在那个 Jupyter 上直接测试，但是不知道就是您就是那样。
Lab 更简单了，就是之所以用 Lab， 我们还有一个原因用 Lab 是因为 Project 我们不提供有限性测试，因为那个代价就比较大。Lab 那个你可以无限测的，所以说你就没有任何 nothing， 就是但是你自己本地肯定要先测试一下，因为这是个好的习惯嘛，就是你肯定自己先测一下，然后你尽量用 Lab 系统的自动测试功能嘛，
就用那个上传的时候
上传自动就有那个了。就是我们这个另外给咱也就是我们到时候 project 的时候，我们就会限制次数，比如说你一个人只能测试20次，那这样的话就是因为各种各样原因了，因为我们那个
那怎么能跟 tutor 沟通一下呢？
那你在 forum 上可以问啊，然后我们周末有，但周末那个人周五那个 tutor 他不一定很熟，但是就我说的就是简单的这种问题他应该都能回答，就是说他大致知道。我们这边就一个 tutor 不是中国人，其他都是中国人。
哦，那太好了，我英文还不行。
然后，当然你在 PS 上面就不要拿中文提问，就影响不太好。对，但是怎么说呢？但是如果你真的要的话，我们 off record 你可以就只像那个只像 tutor 或者我，因为我和 tutor 都在上面都是 admin 嘛，就相当于
在哪儿？
你在 PS 上面可以发一个叫 private tickets， 就只有你可以指定你，比如说你随便开一个你再发一个 post， 你这边可以选是给谁看到，你看你就只给 instructor 看到，就只有我和那个 tutor 能看到，这样的话你就可以。但是我还是觉得你既然到这边来，就尽量学习用英文写吧，因为说难听点，你如果在这工作，你肯定要学用英文书写，不然的话很吃亏的。你在国内说难听，你有很多各种各样需求，你需要 writing in English email 或者是跟人家negotiate，所以说你能锻炼英文，几乎有什么不锻炼了。
那能跟 tutor 约一下吗？就是约一下时间嘛，因为我有点着急，我现在2问都没有写出来。
我就跟你说吧，就是实际上那个管那个 lab 的那个 tutor，现在都被关在国内的。 你回国的话可以跟他们约，我不干涉。
那现在在这面的有 tutor 可以？
有，这是我说的。现在这边 tutor 是正好没回去那位同学，然后他虽然不管那个 lab， 但是他应该完全没有问题。但是就我说你现在什么问题了？你现在问题我们都帮你解决了。
可是那我先看看 token， 看完我下不下课再问问你那个 token， 因为我都忘了，就是那个。
其实没有关系，就是你要 pass 我，我跟你说就是。
做不出来，
就是
做了一天了，
不是你那个 next， 你那个说你不知道这个函数什么？第一个伪代码都有了，你必须得有。你说难听点，就是说这个代码又不难看懂。这个本质上，那我说实话的话，就是说明你编程经验不足嘛。
对对对。
然后不足的话，你随便你就用我们那个example输进去，你看它调用的时候，你既然都用PyTorch 可以查遍，一步步走的时候可以看内部变量啊或者什么之类的，就是说有多种方法，你可以知道这个函数在干嘛。函数你知道它怎么，你看几个 example， 你知道它是干嘛的。你不 try it， 就我说的，你水平高的话，直接看代码就知道。像你，就是我说的，如果你有编程经验，你一看这个名字和我前面那个说明，你就知道这个大致这个东西在干嘛的。然后你再看一下那个 source code， 就知道它是不是在做这件事情。然后你还搞不清楚的话，你就拿些 string 喂进去，看它怎么样，它每步在做啥事情。
那怎么操作能？
这个是 Python 基本的问题，你这个程序都写好了，你怎么调用这函数你都不会啊？
会啊，
那不就行了吗？
但是我不行，那我先研究一下。
更不要说在那个，不管我当然我拍枪不懂啊，不是很熟，就是说，那个就拍的 notebook 里面，你都不用写程序，你直接就可以调用那个东西，你知道了？这更简单了，就是你连这个东西都来问我，这是最基本的事情了。它之所以这个东西叫做 notebook， 就是说你上面写好的函数，你只要执行过那个 cell， 下面就直接可以调用了。
行，我知道了，谢谢您。
Okay, let's resume. So we already talk about logic difference in the logic design, and now we look at query language. Again, we just to give you some kind of flavor in the examples, and there is no more detail. So basically, if you adopt a relational model and implement on a relational database, obviously you can use SQL, and there are extensions. Actually, these are, they are also roll-up or whatever. And they are roll-up, there are a bunch of other things which are really system-specific. I think DB2 is the first system to add a lot of things there. In fact, later you will see that this kind of things was, there is a famous researcher called Jim Gray. So you know that there is no Nobel Prize in computer science, right? The highest regarded prize is actually the Turing Award, right? And every year we only have one Turing. It can be awarded to several people. Last year, I think it's the deep learning, Jeff Hinton, Jan LeCun, and Banjo, Joshua Banjo. So basically, there are only 1, 2, 3. There are only 3 guys from database community who won the Turing Award. The first is E.F. Codd, who sort of like proposed this kind of relational, essentially the relational database theory, and then basically we have products. First IBM. Then another one is actually Jim Gray. Jim Gray actually did a lot of things on transaction. So if you compare with, you probably heard about NoSQL, and you probably heard about the change in the meaning of SQL, NoSQL. So originally NoSQL means really no SQL. So they refuse SQL, essentially refuse to use any of the relational database technology. But now more like not only SQL, right? So more like a hyper system, and also it actually reflected both in term, everything, including the store. So one of the things we actually do research is in data lake or polystore, whatever. So if you ever heard about it, because the future, for especially related to our, for example, for data warehouse. So there is a trend to move on from data warehouse to something called a data lake. It's still going on. There are still a lot of problems not solved, but I think Amazon have data lake solutions. Microsoft has Azure data lake support, and also they have another product related to polystore. Polystore is essentially very similar to the data lake. So anyway, major vendors are actually all have this kind of solutions. So the whole idea is that if you think about data warehouse, it's mainly for reporting, and later you can actually do some kind of data mining or machine learning. So data lake, again, there are a lot of reasons, but one of the things is that it relaxes the schema requirement. For example, here we actually need to design the dimension, whatever things, and use the ETL to load the data into the warehouse. In data lake, it's much cheaper essentially you can dump all the data there, but they actually do need to, whenever you want to get value from this kind of data, there are still a lot of data management tasks where you need a schema. So the focus there is really like for example, in data warehouse, you do ETL, which is usually done manually. Okay, it takes a programmer and the domain expert to try many times. So in data lake, one of the things people are doing is that to automatically infer the schema. So if you import an Excel table, right, you don't need to create a database, create a table, blah, 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 blah. By looking at the column head and again, if you think about it, it's not really a relational database. There are more, there are very strange kind of Excels, because in Excel, sometimes you merge two cells into one just to display it or to draw the boundary or whatever. So there are a lot of things that people innovate, okay, sort of abuse the cells. So, and also it's not a relational table because it could be like a pivots, two-dimensional pivots. So how do you organize it? So there are a lot of things, but the hope is that you can actually do this sort of like semi-automatically. And also the end application is not only this kind of reporting or analytical application, but more on the data science side. So basically you want to do some kind of predictive modeling. That's one. The other reason is that people are more and more concerned with privacy. Okay, especially the EU actually have this GDPR. So it's about if a client requests any business doing business in Europe, you can actually request them to, for one thing, delete all the data about you. So you really need to do that. It's a legal requirement. So you really need to have a central repository where everything about this customer is actually stored, and under request you need to delete everything. Okay, it's really like a physically deleted. It's not right. So basically there are a lot of reasons underlying these kind of things, and hence they require different kind of design and different kind of problems. Yeah. By the way, the left-hand side that's for the same query, and the left-hand side is you use SQL. The right-hand side is a multi-dimensional language. I think the most dominant one is called MDX. So you can see that it still looks like still have select from where. But again, the where condition here is actually usually a slice condition. And also you can have filter or whatever. There are more advanced kind. I'm just showing the basic one. So this is, and also from is always from the data cube, and it's only one cube. So from is always from. So from part is much easier. Okay, it's always from. You select something from the data cube, and here it's actually the pivot. So just by reading it, you can see that you are going to put product at the level of category on the rows, and all the measure. As I said, there is a pseudo dimension called measure. You put all the measure together, and I only need the dollar amount. If you want, remember this is a set. You see, the reason we use curly bracket is a set. You can actually say I display measure.amount and the measure dot, I think another one is maybe cost, okay, on the columns. So if you have a measure.cost added to here, you would imagine that this will actually be amount. This is cost. This is actually category 1, category 2, category 3, and these are the numbers. So you would imagine that the output looks like this, right? So you can see that this is much concise than this one on the left-hand side, and also it's more natural. And you can imagine that further on you can have GUI interface where you can drag and drop or click or whatever, and you can easily translate what is in the GUI interface into this kind of MDX. Right? Of course, you can still translate to SQL, but right, if you have an easy way out, why try very hard on the other way? So next, we actually move further down to the physical level. Okay, so how to support these kind of things? So basically, again, we talk about relational database and MOLAP. So basically, there are in terms of physical implementation, you can actually use still reuse a relational database engine, or you make up a new engine which is fully embracing the multidimensional model. Usually, we actually call it MOLAP and multidimensional OLAP server or whatever things. And nowadays, actually, a lot of solutions is based on the hybrid mode. Okay, we'll talk about hybrid at last. So for the relation ones, we start with relation ones, then the multidimensional ones. For the relation ones, for most of the joins, most of the queries, it's essentially a join and a selection query, because you do if you do slice, it's actually a selection on the dimension. For example, if you slice on the region dimension and saying, okay, I'm only interested in Europe cells, you actually do a slice on the using this condition, and it just translates naturally to a selection condition on the in here. It's actually on the custom table because custom have region. Okay, and if you want to pivot on, let's say, this dimension and this dimension, you select these two, right? And then for the measure, you actually can select what are the measure to display. Okay, so so that's basically what you do. Okay, but it looks like we can still use SQL, right? But compared to the normal SQL, the kind of query you actually see in this kind of ROLAP, relational OLAP server, are usually aggregation and the selection. And because the fact table, I mean, because for relational you use the fact table, you use the star schema typically. Fact table is very large, so the whole idea is that, for example, if you want total sales in Europe for each of the past, let's say, 5 years, and for each product category. Okay, think about in the fact table, if there are 100 million tuples about all the sales, and you do business in, let's say, 3 continents or 3, let's say, Asia, Europe, and USA. Let's say 3, and with similar amount of sales, right? So essentially, the previous query, because the only slice is on the region, which is Europe. So essentially, you need to go through approximately 33 million tuples and do the aggregation and do the group by. Okay, that's going to be really, really hard. So, so we are actually looking at things that we specially designed for OLAP data, or you need to enhance the relational database to support these kind of things. And actually, many of the things stay with relational database. So nowadays, you actually bitmap index and the join index, whatever, is actually widely used in relational database. Even I think Postgres, they starting from version 8 or 7 point something, they support bitmap index. So even for the open source versions, they do that. So we start from the simple query, easy to deal with query to the harder query. So simple query means it's still an aggregation, but with a lot of slice or dice. So basically, you only need to aggregate a small amount of data. But the problem is that over 100 million tuples, it's a huge table, right? Even if I'm only getting 1,000 For example, I'm selecting product category must be food. It must be made in this store, and it's in the last 3 days or whatever, let's say. Even if there are only, let's say, 2,000 tuples, but it's actually usually scattered around in the 100 million tuples. So if you know the details about database, basically most of the data should reside on disk, okay, or SSD or whatever. SSD is much better, but the whole idea that because the sheer volume data, most of the data are still on the disk. So if each of the tuples on, let's say if the 100 million spans over, let's say 10,000 page is actually the physical unit we actually read from data. So we actually want to avoid fetching a page if there is no data which qualify to our query, right? So that's the whole idea. So the most common way to deal with this, even in the relational database, toolbox, is actually to use an index. And here we actually use something special called a bitmap index. So you probably heard about hash index or B-tree index, right? That's the most common kind of index. So most of the common index, for example, if you have a student table, right? You have, let's say, student ID, name, whatever, right? So you can actually build. This is called name. So you can actually build an index on name, and by default, in most of databases, they build a B+tree index. So what does B+tree index do? It actually, essentially, it's a tree where the leaf node are each and every names. Okay, just imagine that for whatever reason, it's not real person name. For example, this name is ABC. The second person name is ABK, then followed by ACA, blah, blah, blah. So the leaf names, these are individual names. They are actually sorted. B-tree by default keep this sorted. And each of them actually link to a sequence of TIDs. TID is called the tuple ID. It's some kind of internal identifier for each and every tuple. For example, there are 3 people named John, right? Let's say, or in this case, ABC. So basically, it's actually sort of like, it's not a really linked list. The actual implementation is much more nuanced because they also need to deal with deletion or whatever updates. But the conceptually, you actually have a linked list of the tuple IDs. So this tuple ID could be the first tuple, it could be the 7th, and this could be the 5th, let's say 115th. Okay. So basically, with this one, you can actually locate the right place on the disk to read off this tuple. Okay. So if your query condition is like select name equal to ABC of this student's table, basically the query processing will actually come down, traverse a tree. It's a tree, basically the guided search to the right leaf node. And then you read off this list. This is a list. Okay? List of TIDs, tuple IDs. And then you only need to fetch these guys and do the aggregation or do whatever things. Now, the bitmap index essentially changed this list into a bitmap. So that's the only difference. Okay? And there are some kind of slight change here as well, because later we'll see, okay, because usually you use bitmap because the number of distinct values here is very limited. So limited that you don't even need to use a tree. It's probably no more than 10 different values, right? So you can just keep it in one block. Anyway, so what is a bitmap? If you ever use C programming and if you have some experience, you definitely use the bitmap. So basically, for example, the general idea that for this table, let's say if you have 1 million, to keep it simple, okay, I use a small number. If you have 100 students, okay, 100 students. So a bitmap is going to be 100 bits So bits is the smallest unit, right? So how many bytes are there for 100 bits? This is 100 divided by 8, right? Roughly, let's say 13 bytes. So this is actually big B. This is a small b. And nowadays, I think most of the architecture is 64 architecture. So this actually means each of the computer word actually contains 64 bits, which is 8 bytes. So this is actually 2 words. And most of the CPU instructions process unit is actually 1 word, because they read off the address and the register is at least 1 computer word width. So the general idea is that so 1 word, for 60 bits architecture, when any of the CPU instruction deals with at least 64 bits. Okay, and if you want to do any bit manipulation, which is AND or XOR or whatever things, or masking or whatever, there are actually a lot of low detail operation CPU can do. It's only taking 1 clock, one CPU clock. So that's actually very, very cheap. I'm talking about most of the bit operation. If there are complex operation, it takes a few more clocks. Yeah, and it's highly parallel. Not to mention that if you ever do game coding, if you ever code a game engine or whatever, you know that you actually can use some advanced CPU instructions. Actually, I think the latest is it AIX? Previously, there are different kind of acronyms. Previously, it's MMD, and there are different kind of advanced things. But basically, what they do is that they actually have super long register and a special instruction to do a lot of fancy things. Okay, so if you really want to squeeze the last bits of performance out of whatever algorithm, for example, it's not game. For example, in bio, they need to do, for example, for the COVID-19 virus, people are actually trying to use some kind of screening to find the possible drugs which, for example, it was designed to deal with other diseases, but based on some criteria, they might be able to help a little bit. So what they do is that they need to do computer simulations, trying to filter out from, let's say, hundreds of millions of known chemicals and whatever things. There are a bunch of very sophisticated criteria, but basically they actually specify a few conditions and the similar, usually it's called a similarity kind of query, and they screen all these kind of things. And then for the shortlisted chemicals, they run through some kind of 3D and I think chemical, physical, whatever process to understand whether this works. Again, I don't know the further details, but the whole idea is that they actually use a lot of this kind of bit operation. In fact, there is a public dataset called PubChem. That's the public repository for known chemicals. It's a public dataset you can download. So I think for each chemical record there, so there you can see there are whatever, a lot of things, but they also have something like, I think around 900. It's 800 something, 900, but most of them are binary. For example, basically there are lots of binary attributes. Okay, so essentially it's a bitmap. So essentially whenever you do this kind of filtering for the medications, you actually can specify a condition on the bits. But the whole idea is that even if you have 100 bits, it's going to be very few computer words, which translate to very few operations. So so if you want to find all, so basically if you have 100 bits, okay, let me see. So if in our case, all the numbers you have is actually 1, 7, and 115, 150, right? So what you do is that you actually put 1, because, let's change this to 3, okay? 1, this is 0, 0, 0 all the way until this is actually 1 on the 1/5. Yeah, we only have 100 bits. So let's say this is 50. So let's say somewhere this is 50, this is 100, so this is 0, this is 1, and everything else is 0. So the bits read like 101 all the way 0 to the 15th bits is 1, and everything else is 0. Right? So based on the position, you can easily work out which tuple it refers to. Okay? And the space-wise, it's fairly compact because in database, this kind of TID typically takes 6 bytes, if not more. Okay? There are certain reasons. Basically, you definitely have, essentially the TID is a page ID plus slot ID. So typically 4 plus 2 at least. For large system, it's going to be even longer. So this is 6 bytes. So even for 3 guys, it's going to be, even if I don't care about the links, okay, it's going to be 18 bytes, right? And here, how many bytes we have? We only have 13 bytes. So we actually are smaller, right, if you use bitmap. So you can actually work out when bitmap is going to be smaller than the corresponding list. Okay? You will actually work out that if the distinct number, for example, if we have 1 million, 100 million guys, and if you have only 10 different names for whatever reason, okay, each list is going to be 10 million long. You can work out how much space it takes. And you can work out how much space it takes for the bitmap. And it turns out that there is a threshold. Usually, if the list is long enough, bitmap actually excels. Okay? That's a very simple mathematics you can do. The other reason is that whenever you have bitmap, for example, you have 1 0 1 1 0 0 0. So this is actually, you can build a bitmap on one dimension. For example, you build a bitmap on region. So in other words, for each distinct value, for example, Asia, Europe, and America. So there are only 3 distinct values. Again, this is a small example, but you can imagine that the region at most is no more than 10, right? So no matter how many hundreds of millions tuples are there in the fact table, basically, or on this is a dimension table. This is a customer, so you might have tens of thousands of customers. They are definitely have no more than let's say 7 different regions. So each one is going to have a very long list, and you can actually entirely use bitmap. So you can see this is the bitmap. The reason we use 5 here is because the table only have 5 customers, but that's just for illustration. Okay, the good thing is that now if I want to say, okay, I want the sales of all the customers in Asia or Europe, right? This actually means you actually only need to take these 2 bitmap and perform a logical disjunction. So OR, in other words, it's logical OR. Okay, and this actually can be done very efficiently because the computer can process 64 bits in parallel. Not to mention that it's easily you can use the super wide register to do it even more faster. And also the whole thing is purely, can be completely pipelined. The access pattern is so, I didn't mention, another thing you can squeeze the last bits of the performance of the code is actually trying to remove the cache stores. So basically, there are L1, L2, L3 cache, and also TLB miss. These kind of stores essentially break the there are also branch prediction errors. So basically, there are a lot of things. If it's just like 2 long bitmap doing any kind of logical operation, the code is going to be super fast because there is sort of like no red traffic, no red light, no traffic, whatever. It's super smooth. And this also works on, for example, if you build another index on type, here type only have 2 or 3 different, let's say, other. You can have always have an other. Then you can actually say, okay, what's the total sale for retail customers in Asia? So it's an AND condition, and this corresponding to AND you use the logical AND between two bitmaps. And again, this can be done very efficiently. So finally, doing these kind of things, for example, if the final bitmap is something like this actually means out of the, again, this is a small example, out of 5 customers, I only need to load the first one, the third one, and the fourth one. Okay, I can skip, I don't need to load the information for all the other customers. So this actually is a great saving if you really have tens of thousands customers and your selection condition is selected enough, like specific enough to select only a small percentage. The other part is that you actually can do bitmap. So there are several usage of bitmap index. So here we actually use the bitmap index on the dimension table. Okay, so we can actually use it, but dimension table is not the biggest part in the data warehouse. I mean the star schema, because most tuple is on the fact table, right? So here, each bit actually means whether the first tuple, for example, the first bit means whether the first tuple in the dimension table customer satisfy the criteria or not. Okay, but what we really want is actually whether the first tuple in the fact table, because there are hundreds of millions or even billions of tuples in the fact table, satisfies a particular criteria. And you can do this by using, it's also, there are different names. I mean, some places called join index, but to be exact, it's actually called bitmap join index. So what you do is that, for example, the following is the syntax in Oracle. As you can see, this is already supported even in the ordinary relational database. So you create a bitmap index. This is its name. You can actually call it whatever names on this cells. And so this is the key. So this is actually the V is actually the key. So you actually index all the different custom regions. So again, let's say there are only 3 regions, and from the whole thing, whole thing here. The whole thing here is a join between sales, which is the fact table, and the customer dimension table. So conceptually, you actually have each and every sales transaction attached on each transaction, also all the customer informations. And one of the customer information is actually the region he or she lives, right, or comes from. Then, essentially, because you create a bitmap index on the joined results, right, naturally, and the joined results number will actually be the same as the fact table number, because it's a foreign key to primary key join. The number will actually be determined by the, you can think about this as like a right join or left join, outer join, but essentially, there is no invalid foreign key. Okay, you don't really want to have a sales transaction with certain amount and whatever cost, but you can't identify where this happens or on what day it happens. I mean, so all the foreign keys are valid. So the number will actually be exactly the same as the fact table. So look at this example. So after doing the join, essentially you attach, whenever you have C1, you have Asia, you have retail. Okay, so this is Asia, retail, Asia, retail. So this is customer. So this is the join results between customer and customer. So I won't fill the other values, but that's the logically what you have. Then on this join table, you do a bitmap index on customer. So that's why you actually need to look at, for example, here, the fact table actually have 1, 2, 3, 4, 5, 6, 7, 8 tuples. So the bitmap will actually be 8 bits long. So you can see 4 by 4, right? But conceptually, you build a bitmap on the joined results. So that's why it's called bitmap join index. But some places they just call it join index. This is because there are other implementation of join index, especially in relational database. There are other ways to. You can actually use a list or other ways to organize join index. But in data warehouse, typically we use bitmap join index. Okay, the other part, which is different, is that not only we need to use these kind of things, we also need to deal with the case where we need to change the query optimizer. Okay, in relational database, you issue a SQL query, and they internally consider different ways to do the operation. Whether I do selection first or I do join first or whatever things. For example, it's not always a good idea to do selection before the join. I mean, usually think, okay, whenever I have some selection condition, for example, here I have a selection on the city, I probably do the selection first, then do the join. But for example, if the data is already sorted, or I mean sorted, it doesn't matter. If there are some certain kind of index where the join actually can use index nest loop, a particular join algorithm. If you do the selection, then you lose the index. So that's one possible reason to do that. Okay, by the way, there is another join index. As I said, I mean, that's the same thing as this one. Essentially, I won't go into detail. But the difference is that instead of saying Asia is a bitmap, you actually use the tuple IDs. So you essentially, you actually record the first tuple in the fact table, the second one, and the fourth one, and the fifth one. So you actually use list. And that's why, again, whether you have this one or not, it's no problem. But for join index, because you might have many values, so you sometimes, I mean, depending on the value, I mean, the attributes you actually index, depending on how many distinct values you have, this is actually optional. But then what you do is that you actually have a list of tuples. Okay, so another way to think about it is that as long as you have Kingsford, for example, for locations, you probably have thousands, I think maybe 4,000 different suburbs in Australia. So each one actually corresponding to different rows or different tuples in the fact table. And if you list them as a list, then this is the join index. But if you can convert this one into a bitmap, then this is bitmap join index. Okay, so the previous two guys actually works by doing the indexing. So indexing will fail if you have a selection predicates which is actually novel, which is ad hoc, which means it cannot be satisfied by any of the index you build, because you can't build all sorts of index, okay, because of space and update reasons. So for example, if I want to find all the cells for whatever strange purpose, my hypothesis is that if the location suburb name actually ends with Ford, it will have better cells than, let's say, location ends with field, for example. Anyway, let's assume that we have a strange idea like this, and we definitely need to do the aggregation, and maybe we do the average or whatever, then do the comparison. So this is actually a regular expression, right? So there is no index can support it. So just to answer this kind of things, we can't use any of the index we mentioned before. So we have to do the selection and do the join. And it turns out that in data warehouse, because this table is so heavy, means majority of the data is here, we actually need to do a join in a special way. This is called a star join. So in star join, what you do is that, for example, the query, I want to write it in SQL, but the query, for example, what we need to do is that we actually have selection station. Again, this is a very strange kind of condition. Again, it makes perfect sense to think about what's the sales during the holidays or during school days. Think about the restaurant on Kingsford, right? So their revenue definitely will be different on school holidays, including university terms versus during the terms, right? And also you have selection condition on customer, you have selection condition on location. So basically this is abbreviated as you have some select conditions, sigma 1, sigma 2, and sigma 3 on each and every dimension. And then you do the join and you do some aggregation. So that's the key part. So the traditional way to deal with this kind of query is to figure out a way to do the join. And most likely, they are going to think about which one out of the three guys, which one to do first. And then they have to, let's say if we choose to do the selection on time first, you end up with a few days, which are school holiday, right? And then you actually have to join with sales. you can't join it with, let's say, customer. The reason is that if you select anything from time, right, the schema will be something like a time ID and all the days, weeks, whatever information. If you want to join with customer, the schema of customer is actually customer ID, customer information, or these kind of things. There is nothing in common, right? So the join actually becomes something called a cross join, or Cartesian product. So in traditional relational database optimizers, for a lot of technical reason, main reason that this kind of plan involving the cross join is actually probably not going to be very good. In fact, anyway, I won't talk about the cross join. So basically, they will actually have to join with cells because that's the only thing you can join with. But in star join, what they found is that they actually do the, you can see the plan. The plan is that do the selection on each dimensions and then really do the cross join. This is the cross join. So cross join will give, essentially, there is no filtering power. You try all the combinations. So basically, if you have 2 choices here, and the 2 customer here, and the 2 location here, basically this will actually result in 8 tuples, 8 combinations, right? So you can think about this is all the possibility of selection conditions jointly on time, customer, and the location. So this one, again, because if you really have selected condition on this one, let's say even if this is 100, 100, and let's say 10, it's going to be 100K, right? 100K, and each one is only a key. Key could be 6 bytes or whatever. Then it's only times 18 bytes, right? So this is going to be 1.8 megabytes. It's small, right? Your phone definitely have more than 2 gigabytes of memory or whatever. So basically, again, let alone a data warehouse server or OLAP server, it's supposed to be super